For anybody who expected to see theory from me, this is going to be a disappointment because there is zero theory in this paper. Zero, absolutely zero. And the good thing is that now I can blame everything that Alex said on my co-authors. However, although it's not theory and it's not finance, it is about big data. So the emergence of big data and big data technologies have really, really transformed every facet of our lives. And I've been working on many dimensions of this. This is a different dimension, different from the ones that I usually think about, which is about news consumption. So what has happened by this rise of digitization and like very fast technologies and AI and machine learning, it means that social media has become a really essential information channel, and a lot of people get their information mostly from social media. And the issue, for better or worse, there is very little editorial oversight on it. And on the bad, I'm sure there's a lot of good sides. That's not what I'm going to talk about. I'm going to talk about like a bad side of it, which is that the emergence of these consorted disinformation campaigns that threatens democratic discourse. So currently, there are two main ways to basically identify and hamper disinformation. There is real-time content moderation that, like Facebook, for instance, does, and there is exposed debunking. Both of these things have like very serious issues. The issue with real-time content moderation is that one, it's extremely costly because it has a extremely high labor cost, and also still it's kind of slow. The exposed debunking, the serious problem is that it's a very low impact, and there's a lot of papers that show that. And the reason is that there is enough evidence that information spread is exponential. News spread is exponential. And so by the time that we debunk the news, it has gone viral. It's too late. Okay. So what we do in this paper is that we come up with this thing, which we call NDL, which means network-based disinformation labeling. And I can talk about, like, I want to basically think about the talk in two steps. First is how to detect the disinformation. As I said, there are the two main ways that are used to detect disinformation are both content-based. One is content moderation and then exposed debunking. What we suggest is to classify accounts which are agents instead of the news, which is the content. So right now the methods are mostly content, but we suggest to go into for the accounts, and this is hard. Why? Why is this hard? Because if other accounts knew that I am an account who's spreading disinformation, of course they're not gonna look at what I say, or they're not gonna spread it. Okay, so naturally disinformation is spread by accounts who are trying to posit themselves as good guys. So it's hard to identify them. Then let's say, for the sake of it, that we classify these accounts. Then okay, then what we need to do is that we need to statistically tie back these accounts to the news. And this is by itself hard. Why? Because these disinformants often have to spread through news. Why? Because if they were always lying, someone would have identified them and they would have been ignored. Okay? So both of these steps are not obvious. Then let's say even we did it, okay? Then you're gonna ask, okay, fine, you did it, and you did this like conceptual question that's like game that you wanted to play. Now, what is the impact of this thing on disinformation consumption? You're concerned about the rise of disinformation consumption because of lack of oversight. How are you impacting it? And for that, we're going to use something like, I'm going to call it a natural experiment because I'm a theorist, I don't know what it's called. A natural experiment, which is about debunking disinformation to get some estimates of the impacts. And then we're going to use that estimate to run simulations in the context of our model. So I know that was like kind of unclear, but if I want to clarify it without talking about my data, it's going to be even worse. So let me try to tell you what data, because this is not a theory paper, okay? This is literally like, we're gonna do something and use it on the data. So I wanna first tell you about the data. The data comes from Twitter, at the time Twitter, now X, and it's from the period of this protest in Iran called Women Life Freedom. They started in September 15, 2022, and the data is until the day that Elon Musk shut down Twitter API. So in March 2023, these protests started when a young girl was killed in the streets, unintentionally, intentionally for lack of head cover by the militia, and then people got kind of very unhappy, and then they went to streets. It was like completely like harmless protests, but then this happened multiple times, and because Iranian media is completely controlled by the government, people took it to social media, to Twitter, okay, especially because also internet speed is very low, and Twitter, because of the small size of the messages, it's very convenient. So on this plot you can see okay, so one thing that I should have said is that we, of course, at the time had not thought about having this data. We just happened to run into our two great co-authors, Leila and Stephen, who has been collecting Twitter Farsi data by post for like 2 years before this, and they were willing to share their data with us. Okay, so thanks to them. Sorry, I forgot to say that. So from this plot you can see from June 2022 to when the data ends, mid-March 2023, and the y-axis is basically in terms of millions of posts in Twitter Farsi. Okay, you can see that on September 15th it goes off the roof. Okay, and this is where the girl was murdered, and then of course it's been falling. It never went down as it was, but still. So this period was really a period where social media was heavily being used. So now let me tell you about the data. We have kind of three. We collect this data and then we merge them. So the first one, it comes from Twitter or X's prior V1 and then V2 API. This from here we get all the posts and the accounts. So what does a post object in Twitter look like? A post object has like a lot of things that are about the post itself. For instance, there's a unique ID, there's a text of it, there's timestamp, and there's a bunch of public metrics like number of followings, number of retweets, and stuff like that. Then there's a creator's account ID, the username, and some public metrics about the creator. For instance, how many people follow him, how many people he follows. Then more important for us is that each post has, so when you see a post, you don't know the posts that like follow it or retweet it, okay? But from each post, there's a reference to a post if the current post has engaged with a different post. So if like I retweeted something in my post, there is a reference to the person who I retweet, to the post I reposted or quote posted or replied to. And also there is the ID of the creator of that post. There's a history of following interactions that you can find. So from these two, we can basically create the full network of all the active accounts. I'll tell you what active accounts is. Let's say all the accounts on Twitter Farsi and their interactions. And the interactions that we have in mind are 4. There's like following, follower, which are the reverse of each other, and repost and reposted. Okay, and I have both of them, all 4 of them, because the difference is going to be meaningful for us. Then the second thing that I'll say is what do I mean by an active account. The number, I'm going to show you numbers, but the number of people who have ever posted in Twitter Farsi is huge. So we're going to limit our sample to people who have at least 10% of their posts in Farsi. And during this period, after the protest, they have posted at least 10 times in Farsi. Okay. So from 9.5 million accounts, that takes us down to 1.7 million active accounts. So you can see, so this is kind of this, just to convince you that cutting down this account is not really impacting anything. Look, this is the first block is my full sample. The second block is my active accounts. The biggest cost is the number of accounts. The full sample has like 9.5 accounts who have ever posted in Twitter Farsi. The active accounts is like 1.7. Okay, but everything else, okay, does not, changes between the full sample and the active accounts, but the number of posts falls 5-fold. Everything else falls about less than 20%. Okay, so for instance, the number of posts sent in the full sample is 83 million. In the among the active accounts, it's like 62 million. Okay, so it's about like 4/5 of it. And also, in these two columns, I'm dividing it before protest and post the protest, and you can see that the same thing. For the number of replies sent post the protest by the whole 9.5 million people is like 13 million, and by only the active people is like 12 million. So really, I'm not cutting much of the interactions by going down to only the active people. So that was the first part. So the first part of the data is all the posts, all the users, all the connections between them. The second part is that I'm interested in identifying disinformation. So I need to have a notion of disinformation, okay, and legitimate news. So what is a disinformation campaign or event? I'm going to use campaign and events interchangeably. And disinformation event is a piece of news whose initiators were aware that it was false, but they started spreading it on a social network intentionally. Okay, so now with this definition in mind, we collect two sets of news. Okay, all in this period. Okay, so we're gonna collect 14 exposed with verified disinformation event. But what do I mean by exposed verified? A lot of this information was like, there was a news saying person X was also killed. 2 weeks later, person X would come on TV and say, "Hello, I'm alive." Okay, so the exposed debunking was, or like, this judge is killed by the people who are protesting, and then the judge was alive. Okay, tomorrow he will be seen in court. So that is like the debunking is verified that it's debunked, and then 10 exposed verified instances of related legitimate news. So 10 news that are true. So what do I say by related? By the way, I mean, first, the context is about the protest, but the main selection criterion is the similarity in content, meaning for an outsider, it would be challenging to distinguish from the content alone whether these news are false or true. Okay, and I'm doing that to make sure that it's not by content. If you do this, it's going to be tough. It would really need exposed debunking. Then the toughest part, and this is thanks to Jesse Shapiro, who forced us to do it. So we manually identified and collected about 1,500 organic rebuttal. What do I mean by organic rebuttal? Organic rebuttal is engagement, usually by Iranian social media activists who went on the social media and basically engaged by this disinformation posts, okay, and said, okay, they're wrong, okay, and they basically contested the validity of them. So we have 14 instances of disinformation. We found these rebuttals only in 10 of them. Okay, it might be more, but this is what we found. So that's the second piece of data. So the second piece is the actual news. And the third piece is I need some training data. Why do I need some training data? Because as I said, my target is to try to identify this information from people. okay? So I would need, my goal is to classify active party accounts into 3 groups of people, okay? And these 3 groups are context related. If you want to do a different context, you have to define the groups depending on your context. So the most important group is unsafe, who are these covert accounts who are already or have or will actively participate in the spread of disinformation. Okay. The pro-regime are these accounts that publicly say we are pro-Islamic Republic regime. It's obvious from their name, from everything. That's easy. And third one is ordinary, like normal accounts. Okay, like you or I, and we might engage in disinformation because we don't know. Okay, not intentionally, or we might not. So my goal is to classify all the active users in these 3 groups. So in order to do that classification, I need a classifier. And my classifier needs to be trained and tested. So I need training data for that classifier. And so we're going to collect about 1,500 labeled accounts, labeled as one of these 3. And we get help from activists to do it. So about 500 are unsafe, ordinary, and pro-regime. We use 70% of it for training and 30% of it for testing. And then in one of our sanity checks that we do is that we hire a second group of experts or an activist to validate this test, this check. Okay. So these were all the data. So the last thing that I tell you before I move to my model is that we're gonna, as I said, we're gonna use a classifier to classify the accounts. Classifier needs characteristics. Okay. So we're going to use a bunch of basic characteristics, which are kind of obvious what every model would use, which are like age, posting rate, number of followers and followings, basically follower to following ratio and stuff like that. And then, but more importantly, and what is really crucial for us is that we're going to construct what we call network-based characteristics. Okay. When you hear network characteristic, you might think about centrality measures, okay? This is above and beyond centrality measures. We throw whatever centrality measure that you want also in there, okay? But when I'm talking about network-based characteristics in this talk, I actually don't mean centrality measures. I mean, these are measures of proximity of each account to the groups in the training sample, okay? These proximity measures are stuff that computer scientists have been using forever. So for each, so here is what a proximity measure is. Take a pair of accounts, U and B. So I want to think about 4 different relationships between these two accounts. First is following, means U follows B. Second is follower, means U is followed by B. Then reposted, U has reposted a tweet from B. And reposted, U has been reposted by B. Okay. So then this proximity measures basically inductively find whether there is each of the proximity measures, find whether inductively there is a following relationship between a particular given amount and anyone among the unsafe in my training sets. Okay. Whether there is a follower measure, what is the follower proximity measure of anyone in the, for instance, pro-regime or unsafe accounts in my training set of a given person. Okay. And so there's going to be 8 of them because there's going to be one for each 4 of these measures, one for one for the unsafe accounts in the training sample, and one for pro-regime accounts. Okay, so effectively, what they are capturing is some meaning of shortest path. Okay, which is a feature of the network structure, which is basically in a network sense how close each of my accounts are to the verified agents who are disinformants and pro-regime. So why would this? So you're like, okay, why are you doing all of this mess? Okay. And the reason is what I said in the beginning. The bottleneck in fighting disinformation is speed of detection. Okay. So this proximity measures heavily help us identify accounts that are unsafe. What do I mean? An unsafe account, even if he has never posted something and which is a disinformation, turns out to have close proximity measures with the unsafe accounts who are already established. Okay, so that is basically they have engaged these accounts who have not, these unsafe accounts who have not engaged in disinformation spread yet. They have engaged heavily in these proximity relationships with the unsafe agents who are identified. Okay, so that helps me very much when in my statistical pattern. Okay, so now let me tell you how we do this. The way we do this is NDL, network-based disinformation labeling. It's a two-step procedure. The first step is the classification step, which basically trains the account classifier using the training set with the verified types, and then classify all the accounts using the training model into the 3 groups. So every account is going to be either unsafe, ordinary, or pro-regime. And what is the rule? I need a rule. The rule is this is going to be it's a classifier, so it gives us propensity scores. I'm going to assign each account the group with the highest propensity score. Okay. Theoretically, you can do an average or whatever, but we do it at the max. Then there is a second step, is the statistical step, which basically uses the accounts who have engaged in the piece of news to label it as disinformation or true news. And this is the toughest part. I need a statistical rule. The rule is of this form. And this, we tried many things and this worked. Okay. I don't have any proof for it. If enough of initiators of a news are disinformants, are unsafe, we're going to call it disinformation. Okay. Enough in particular for us would be out of the first. So remember, I can step back every news to who started it first. Okay. And from the first 10 people who started each piece of news, if 7 of them are labeled as unsafe by my classifier, I'm going to call that disinformation. So the classifier is a multinomial logit. It has really great precision and sensitivity. The pro-regime accounts is almost perfect, but there are mistakes between ordinary and unsafe accounts, both type 1 and type 2 mistakes, but they are both better. We perform both better than 90% in all of them. The important observation is that really all the work is done by the network proximity scores. If I take out the network proximity scores, even leaving in the network centrality measures, my overall accuracy is going to go down to 75%. Okay? Then, so let's forget about this. We're going very short in time. Then, what about the statistical disinformation labeling? This is the rule that I said. We call it network-based disinformation labeling. NNM means a piece of news is labeled as disinformation if and only if in the baseline model classifies M out of its first N initiators as unsafe accounts. Okay. So what we're going to do is that now we're going to train the classifier only with the verified accounts of the first 6 disinformation. Okay. So there's like 14 of them. We're going to take disinformants from the unsafe accounts who are only involved in the first 6. We're going to retrain it. And then we're going to label all the 10 legitimate news and the 8 remaining disinformation using only training by the first 6. And then we're going to try to balance early detection and accuracy. What does it mean? If I push 10 higher and if I push 7 higher, then I'm going to be more accurate. But it's going to be too late. The whole point was to do it early. Okay, but this 7 out of first 10 has a good balance. So this is how we do. So remember, this is like 10 true news, 8 disinformation. On the x-axis is basically the length of the data that we use. The last 8 disinformation campaigns all start after February 15, 2003. So we're not using data from after them. All the data is from before them. So on the y-axis is the percentage that is classified as disinformation. Blue is the average percentage of true news using data up to the date on the x-axis that is classified as disinformation, 0. So we don't mistakenly classify any true news as disinformation. On the other hand, for the disinformation, if we use little data, we are about 85%, so we can make 1 or 2 mistakes. But if we use all the data, then we do perfect, okay? But if I throw out all of my network proximity measures, then it's gotta be a mess. You can see that I make a lot of mistakes in identifying true news as false, as disinformation. I also can misclassify a lot of them, of the disinformation. So now, hopefully you're convinced that my model does well. Now let me tell you, how do I measure the impact of disinformation? So I told you what rebuttals are. Rebuttals are organically an activist comes and says, okay, this news is false. Okay, this is not true. And then I can measure the impact of it on the disinformation thread. On the x-axis is the minutes to the first rebuttal of each thread in the disinformation campaign. And on the y-axis is number of posts per 15 minutes. Okay, you can see that it's growing up, and then there is a discontinuity. When the first rebuttal happens, there is a discontinuity, and it keeps coming down. Okay, so this looks nice. How am I gonna estimate it? I have to impose some assumptions. So I'm going to assume that the information thread is exponential, is Poisson process with a varying mean, and then I'm going to have a definitive estimate to estimate the impact of rebuttal. So basically the mean is the number of posts is Poisson with a mean, and the mean depends on how long it has passed. Tau ij is the time of the rebuttal of thread I of news j, and tau, and this mu is about whether the time is how far the time is from the time of the rebuttal. So so this is a huge table. You can regress it with millions and millions of fixed effects. The important number that I care about is this minus 2.15. What does that mean? It means that if there is a rebuttal, there's an immediate impact, and the posts per 15 minutes drop by 2, from mean 13 to average 11. Okay, then I'm gonna take this number, this drop, and I'm gonna run 2 sets of simulations. The first simulation is the baseline simulation, which is supposed to capture the average statistics of the realized disinformation campaign. So I'm just gonna follow the actual realization, and the rebuttal happens whenever it happens in the real world. Then I'm going to do my NDL simulations, which is basically supposed to capture the impact of this non-network-based disinformation labeling if it is adopted by the social media platform, and whenever in the first 10, 7 of the initiators are disinformants, every thread there's basically a rebuttal posted on every thread. Okay, so I do basically all the existing threads are rebutted after the 10th one, and then I'm going to compare 3 characteristics. The first one is the number of posts in a disinformation event. Second, the maximum user engagement rate, and third, the duration of the disinformation event. And if this adoption happens, this is the impact on news. So this is the impact of adoption of this network-based disinformation labeling on disinformation consumption across the social media network. So the number of posts in the disinformation events goes down by a factor of 3. The maximum engagement rate goes down by a factor of 2, and the whole length goes down by a factor of more than 2. So it's, forget about robustness. So to me, as a theorist, it looked like that this network-based approach for early disinformation detection has significantly mitigate consumption of this information on the social media. And it's important, especially when the spread is intentional.
It's a cool paper. Here's how I would summarize what's going on. So they're interested in labeling and sort of stopping, disinformation. The hard thing is doing it quickly, right? And so they sort of like leveraging a simple but sort of cool insight. It's basically like, look, it's super easy to go and create a fake, Twitter, X account, whatever you want to call it. But if you want to use that account to go and tell people lies, right, you need to have people actually listening to you, right? You have to have followers. And it turns out that the way, people who want to spread disinformation attract followers looks different than the way you and I do it, right? Ergo, it's possible to go and look before they actually spread it into disinformation and try and see whether or not someone is likely to do so in the future, right? All of this can happen before the actual disinformation event. They go through and estimate with like a network-based model and figure out who these people are, and then they flag posts that are clearly disinformation whenever there's some critical mass of the first few posters is one of these flagged accounts, right? And something that's sort of not talked about in the paper and is sort of I think cool about this approach is, suppose you end up on this disinformation list and you're like one of these unsafe accounts by accident, right? Well, nothing happens most of the time. It's only the case if you try to sort of post and then a bunch of other people who are also on the unsafe list post along with you. Right, so this is not like a no-fly list where you get turned away at the airport for being on this unsafe account list. It's only sort of kicks into effect when you also happen to post about some fake piece of news, right, along with 9 other people who are also on this list with you, right? And so it's sort of a nice feature that's sort of not highlighting paper might be worth sort of bringing up. So again, cool paper. Not the paper I was expecting to sort of get in the email, but it was like a lovely paper, very straightforward empirics, important real world application. I don't know. The more I was sort of digging into it, something kind of struck me about this. It's hard not to think about fake news, but I hadn't actually thought about the mechanics of how would it spread. And the more I thought it was kind of a weird system, it's didn't fit with this sort of model I had in my head for how it would work. And the thing that really jumped out at me was just so there's this table, it's sort of hidden, there's a bunch of accounts. There's 1.7 million of these things, right? There's about 1.4 of them that are just normal people, right? There's 150,000, 140,000, right, that are, pro-government. There's almost 300,000 unsafe accounts. That is 16% of the sample. It's a wild number, right? And it doesn't sort of fit with the usual story that you would tell for viral spread of information, right? It's almost like a normal sort of people are building a bunch of fake accounts to spread disinformation. It's not about the actual network's reference. Sometimes there's a stock amount of fake accounts that need to be built up. So I want to sort of just highlight how unusual this is from a sort of the typical model you would write down. And what I'm going to do is basically show you 2 examples of the sort of theory you'd write down for this. Go through it pretty quickly and then sort of circle back around to this table 4 number. All right, how do we make sense of this? So first example of a prototypical network account, we just look at Erdo's Renian model. So let me explain what this is. Right, you got a graph, right? It's got a bunch of nodes, and what you're doing is you're basically having, say you've got 20 nodes, right? You have a graph that looks like this, right? The nodes stay the same, those dots stay the same. And then what you're going to do is when each time you sort of create a graph, you do it randomly so that the number of neighbors, right, is drawn from this, Poisson distribution. And mu is the average number of neighbors. So mu is 2. In that case, it would be this node is a typical node where you got 2 neighbors, right? If mu was, 4, it would be this node, we got 4 neighbors, right? So what you can do is just randomly pull a bunch of graphs, right? And this looks like this. And so the whole thing in this model is you want to look at how big is that giant component. And usually, if you got a certain number, your mu is big enough, you're gonna have a bunch of nodes that are all sort of connected together, right? And so each one of these graphs is a big giant component. And so the key thing in these models is it's called the size, or I'll call it S here. It's just the probability if you picked one of these 20 nodes at random that you would end up in that big sort of big bit, right? So here it's about 60%. Right, so there's 12 of those nodes inside the giant component. There's 8 outside. So you get 60%. So the whole point in this setup is you want to figure out how big is this sort of big clump of things as a function of the typical number of neighbors for each node, right? And you can go through and do this yada yada yada. Right, I'll do the theory. Right. A cool thing is you can solve for it numerically. Right, and you get this sort of picture. And the whole point here is, if you've got a bunch of nodes where the average number of neighbors is really low, again, like 0.5, well, a typical node just not connected to anybody, right? So you're not going to have much like clumping together. And there's going to be a sudden change as you get across the threshold of 1, right? So you get like, 1.2, 1.5 or something. All of a sudden, it just jumps up where a big chunk of the whole population is going to be in that big, connected component, right? And so if you get a 60% sort of like the size of the, typically the sort of average number of neighbors is 1.5, right? And so the punchline of all this is like you can get a little tiny change, right, in the typical number of neighbors for each individual node and get a huge change in how connected everything is, right? And so this is like the one way to think about the viral spread, right? If you can kick the system across this line, all of a sudden you get a big change in how many people see the post, right? All right, so that'd be one model. Also, you can get a similar thing if you look at like an epidemic spread model, right? At each instant, you have each sick person sort of infects a certain number of other healthy people. Right, there's a total of 8 healthy people in the model, and now you've got some mu parameter. It's also going to have some like little bit of connectivity. Idea. Let's normalize the sort of average length of time that you are sick to 1, right? And then so you look for the steady state sick person population. Right? I think we've all seen this model like way too many times by this point. And so you go and you compute the sort of evolution over time. The key thing in the setup is that there's a fixed number of people in total, right? So the number of sick people and the number of healthy people is the total population. You plug that in. Set it equals 0, and you get a similar chart out. Right? Again, the whole idea here is that you've got this model where there's some connectivities for each individual, a sick person is going to affect a certain number of, other healthy people, right? And you're varying this mu parameter, and you can have a little tiny change in the mu parameter will give you a big kick in the overall sick population, right? And I'm going to emphasize again that the whole thing comes from recognizing the fact that there's a fixed number of people, right? Some of them are sick and some of them are healthy, and we're sort of using this population size. Okay, so the standard playbook in every model like this you'd write down, right, is you go and you sort of you put like a you're on like a big population of nodes of people or whatnot. You fix that, right, and then you specify some rule for how the nodes are linked, right, and you make it as innocuous and boring and smooth and sort of simple as possible, and then you show lo and behold. Right, when you change some like little parameter, when you go over some line, all of a sudden there's a radical change in the overall population. That's like morally speaking what every one of these models is going to do. Okay, so this is the usual setup for one of these network models. Now let's go look at like what's going on in the actual data. Right, this is like not like a little tiny change in some parameter. Right, there's 1 in 6 with accounts in this data. Right, is spreading disinformation. That's like a really noteworthy thing. Right? Instead of thinking about this as a problem where like there's some like there's a bunch of normal people and then a few accounts that are thinking carefully about how to be connected so that they actually spread disinformation. What's going on is like the people who are responsible are creating lots of accounts probably, right? And going through and just like flooding the system, right, in a way that is like not holding fixed the size of the account, the whole population. They're actually just changing this global structure. It's actually noteworthy, right? It's striking you need kind of like a different kind of model. This isn't like a there's a little tiny change in the parameters. It's like a big shift, right? And this is like just was not how I was thinking about this setup, right? Yeah. So I found like the actual structure here was I appreciate that like the actual estimates are coming from like a network based model, like it's like unequivocally true, like very cool. But like when I was thinking about how I would want to go and like model this, like the usual techniques, the usual tricks we would use would not be the way to go because it's like going after like a like very large tick of the system. Right, and it's clearly changing the overall size of the population that you're looking at. Right, it's not like we're not looking at some like tiny like change parameter. So none of this is to say that like the estimates or anything in the paper are wrong. Like clearly, like there was a debate about there was like a fight over like sort of how to best sort of fight disinformation on social media in Iran at the time. Right, this is a cool trick for doing it. Right, it clearly can be used in other contexts. Like once you have this list of like people who are willing to spread fake information, like you can totally do this. I like the approach, but like it does the actual mechanics of spreading this information were interesting on their own, right? It was like not at all what I was expecting. But cool. That's full end. Thank you so much.